Okay, the next subsection I want to talk about some little algorithms that will be building blocks towards our bigger goal for parallel sorting. And so we've seen the parallel models now. Let's see what we can do with those. And the first little building block I want to look at is called the prefix sums. So it's a very simple problem, but it turns out to be quite versatile in using in other parallel programs. The problem is as follows. You're given an array of numbers, just n numbers stored in an array. And you're supposed to compute the prefix sums, which is just the sum of the first I entries. And we want to do this in place. So we have the array A before, and then we change the array and overwrite the elements with the prefix sums, where at this position we sum up to, well, all numbers up to this position, including that position. Okay? It's an abstract little problem. You'll see in a few minutes why this is useful. But for now, is the abstract problem clear as this? So every cell just contains the sum of all the numbers up to this point. And if there's zeros, for example, here you get repetitions. Also, this will never go down. Some simple observations. All right. Let's wake you up again. Suppose you wanted to solve this innocent little problem sequentially. So we don't care about parallel for now, but guess what? There might be a follow-up question. And how fast can you do this? Okay, seems to go quick. Few more seconds. Three, two, one. Locked. A wide range of different answers. And the majority is right, though, or the largest vote was right. So sequentially, we can easily do this in linear time. And I'll show you how. If you can do one of the faster ones, I'd love to learn. So the sequential solution could be as follows. It's maybe just it's so small that's easiest explained in code. You just iterate through the array, and you compute the next prefix sum by taking the previous prefix sum and add one new element. So you start computing on the left. The left element is its own prefix sum, so you're done. Go one step to the next, to the right, take that element and add the last prefix sum. That makes the new prefix sum. And as you keep going, you notice if you fill the array from left to right with the prefix sums, all you really have to do in each step is add one more element. Easy. That's a nice little code if you want to do it sequentially. That's fine. The problem is you can't really parallelize this one. And the reason is that there are data dependencies between the different steps. Each step depends on the computation that has been done in just the step before. So you can't really pull this one forward. You have to wait till the previous step has done its work. Is that problem clear? The data dependency trickles all the way through, and that prevents us from speeding this code up by parallel processing. So we need a different approach, and luckily there is one. And let's simplify the problem a little bit just to see clear. Instead of really doing all the prefix sums, suppose we're just interested in the last entry, the sum of the entire array. This is definitely solved by the prefix sum problem, because we can just take the last entry. But this is a little cleaner to draw. So if you think about this for a few minutes, you want to compute the sum of n numbers, and each step can only take 2 numbers and add them. There's no way you can get away with less than n minus 1 additions. In a sense, what you're building is a binary tree. You start at the leaves with the original numbers, and then every node can take 2 things, 2 subtrees, and add them. And no matter how you do this, you will always need the same number, n minus 1 nodes. If you want to prove this, there's a nice little proof where you say every node has 2 slots for children and 1 new slot is added. So whenever you add a new node, you take 1 slot away, and that's it. So you need n minus 1 slots away steps before you add 1. But we're not forced to use this shape of a binary tree here. We can use a different one. For example, the one below, the balanced one. And in terms of data dependencies, we want to do this because here the data dependency basically meant following a path. This last element was what we wanted, the total sum, and it depended on this, which in turn depended on this, depended on blah, 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 blah. So we have this long chain of dependencies just in the data, how we compute. And in this tree, it's better because the height of this tree is much smaller. In the small example, not as dramatic, but of course you're experts now. Complete binary tree, log n height, or log n rounded up, whereas the other one has linear height. So that's a huge difference if n is big. So the parallel time here is just the height of the tree. It's a little tricky to write down in array index syntax what this tree looks like in code. But in essence, that's what we want to do, to compute the sum faster. So if you're just interested in computing the sum of an array, what you want to do is simulate this complete binary tree. And you can figure out how to do this with indices in bit magic, taking the numbers, the indices as binary numbers. For the prefix sum problem, we have to work a tiny little harder because we also want all the prefix sums, all the other partial sums. So what we'll do is a generalization of what you've seen for this tree. So this is maybe the first detailed algorithm. So everyone wake up. We do this in steps. Here's the input array. In the first round, every processing element takes its own value and adds the one that is 1 to the left, except for the first one where there's no 1 to the left. So if you trace this up here, 5 and 7 is 12, and so on and so forth. Okay? Now note that in the first step already, by definition, this guy was the correct prefix sum. So this is already settled right from the start. After this first step, also the second element now contains the correct prefix sum, because it only needed to sum up these 2 elements. Okay, so we seem to make progress. Now the question is, how do we continue? Any guesses? You don't have printouts of the slides and cheat, right? You wouldn't, or on the laptop. Well, it's computer science, so it always has to do something with powers of 2, right? So in the next round, every processing element adds its previous value, which is some partial sum, and it goes 2 steps to the left. And this way, the first 4 elements are already correct. And that's on this small scale example, see why. If you look at the 8, that one was supposed to sum up the 4 values in the original array, which is this part. And the 8 summed up this and this entry. And they each were the sum of these 2. And so after the 2 rounds, this position indeed contains the sum of the first 4. And now you can guess the pattern. We keep doubling the distance we go back. So if you go to another round, we now jump back 4 positions. And so after that, a prefix of 8 elements, counting is hard, knows its correct prefix sum. That's still not the entire array, so we have to do one more step, in which case we now go back 8 steps. Okay? And I highlighted here at the end again for one of these elements where its values come from. And you see two things. First of all, if you follow the paths, you reach every element in its prefix, like excluding the last one, exactly once. There's exactly one path to this element. And second, that looks a lot like a complete binary tree, doesn't it? And I mean, it is. We're just simulating this idea with computing just the sum, but we're doing it not once, we're doing it for every position. And we interleave the computation so that it's faster. In terms of the parallel time, we use the same time we would have used for just computing the sum for computing all prefix sums along the way by nicely interleaving those. Okay? Now I've explained this on an example. We also want to be able to write pseudocode down for such parallel algorithms, and that's something we haven't touched on yet. And here's the code for this algorithm that I just described. And you see, it's one code, and that's run on all the processing elements. But there's well, we don't need the processing element index here explicitly. What we assume is that, in a way, every processing element is sitting at one position in an array. But this is not explicit in the code. The outer loop is through the rounds, and we need log n of these rounds. That's the height of the binary tree. Step is how much do we have to jump to the left. And then here's this loop's just saying exclude some part of the array that's already dealt with. That's why we start at step and not at 1. And the important part, of course, here is in red. This is a loop now that we run in parallel. So the idea here is you take the loop body and assign this as a little job to different processing elements, and they run the loop body step by step, line by line if you want, in lockstep. So for each of these values, you first do this step, compute the sum of your value and the one so and so many positions back. And in the second step, you write that value into the array. You might be tempted to take these two statements and make them into one, because that's what they seem to do, right? Because x eventually is written to a of I. But this wouldn't work, at least unless we define what exactly the execution order is. It's important that all the processing elements read the old state of the array first and do the computation based on that. And then as a second step, they write the new values back to the array. Otherwise, you would get some weird mixture. And this is where you see PRAM algorithms make this easy because there's implicit synchronization. If you program this without any synchronization on a thread-based language, then it would create chaos. You get writes that precede other reads and stuff. I hope the code is clear enough up to this point, and it follows the example. So that's your first PRAM code. Now we want to also briefly analyze how good this algorithm is. And we have to do two things: work and time. We ignore the space, that's constant in a sense. For time, we can just treat this wherever it says do in parallel. We ignore that there is even a loop. We just count the longest execution. So I don't know, let's do green for span. So we run the outer loop. This is not parallel, that's sequential. So we run this log n times. But then the rest inside here, this is just one step, and these two are also just one step. So all of this has constant span. It happens in constant time if you parallelize. That's why the span is just logarithmic. Let's use this for work. So What can we say about the work? Well, for that, we basically ignore the in parallel statement and treat it as a sequential algorithm and see how long that would take. If we do that, we see that this part is indeed constant, and this, of course, too, constant time. But we repeat this loop roughly n times. I mean, it's n minus step, but you've seen probably quadratic loops like this before. So it's at most n iterations of the inner loop, and we have the outer loop same as before, logarithmic steps. So you have log n iterations where each iteration takes linear time, so that's n log n. That's what we have here on the slides as well. Now, this is not work efficient because remember, the sequential algorithm took just linear time, and now we need n log n time. So that's not the ultimate prefix sum algorithm yet. And in this case, we can see it as a trade-off. We improve the parallel time, but at the expense of more work, which might or might not be better. In this case, we reduce the parallel time from linear to logarithmic, so it's probably a good deal, even though the work is not optimal. So sometimes you have this trade-off that inherently you cannot parallelize things unless you pay extra in work, but not for this simple problem. Here we can actually get linear work if we just pay twice the time. So the same theta class, but a constant factor difference. That algorithm is a little ugly to write down. So instead, I'll show you a very simple one that uses a much more general technique that will come up in other contexts that achieves the same, but uses 3 times as much span. But by and large, these constant factors are not so clear how much they materialize, so I'll ignore that part. The way to improve the work is to break things into little blocks at some stage and do these sequentially. That's the abstract idea. And this breaking small subproblems into blocks that you treat differently, that will come up in different disguises. So what we'll do here is we use blocks of log n elements. And then we conceptually break the array into blocks of that size. So the first log n, the next log n elements, and so on. And for each of these blocks, we assign one processing element to compute the local prefix sums. So these are just inside the block. You sum up the prefixes. Then we use the algorithm we've just developed, which is has good span, but is not work efficient. But we only use it on a smaller input, namely only on the rightmost entries of each block. That gives us the prefix sums of some positions in the array. And in particular, the last one is almost the sum of the entire array. So we're almost there. But we have to fill some of these intermediate steps only have the local prefix sum. And so what we have to do is to add the block offset in a way. I think it's worth maybe sketching a brief example on this. I'll try to not make it too big. So say we have 3 blocks, and each block has 4 elements. So we have position 0, and then 4, and then 8 at the beginning of a block. And to make things nicely work out, let's say n is divisible by the block length. So then we do this first step, which is the block local prefix sums. Okay, let me fill in the array with numbers, and to make it easier, let's say, and this is not really readable, I'll write the 1 like this. I want an array that contains all ones, because then the prefix sums are very simple. It's just 1, 2, 3, etc. And for illustrating the example, that's enough. You could substitute other numbers, and then the addition is different, but the rest is the same. I think it's convenient to look at it with just ones. The first step was, inside the blocks, compute local prefix sums. And what this means in the example is just, this becomes 1, 2, 3, 4. That's what I mean by local, right? These guys, they don't know that there's much more coming in front. Then for the second step, for the third step, second computational step, we only use the last element of each block. And in a way, we put that into a new array. Say, I want to align it in the picture, but really this is just one fat array, okay? With really huge cells. I mean, and how big is this array? The length of this one is the original length divided by the block length, because we take one element out of each block. And then this step is computing the prefix sums of this green array. Remember, that's what it says here. You take all those and you compute their prefix sums, but using the work inefficient algorithm. So we'll have to see in the analysis how good that is. For the example though, it's simple. It's just 4, 8, 12. And then the last step was to add this prefix, to add the offset here to the original array. So I'll take a copy of this one. And then this last step adds this to all of these. And 8 to all of these. All right. And I made this look like you copy the array. You can actually do it in place, but let's not bother. So for the second block, we add 4 to each, and then it comes out like this, as it's supposed to be. And then here as well, sorry, 8 plus 1 is not 8. Okay. I hope the example makes it a little more clear what's happening. The idea behind all this is we have a good algorithm, it's just not work efficient. So we try to avoid calling it on the entire input. We just reduce the input by some factor first. And we call it on exactly an input of size n divided b. And b was log n. Okay, so it's a log n factor smaller. And that will be just enough so that overall this is work efficient. Let me try to speed this up a little bit. So the second and fourth step, let's first analyze the time, ignoring work, right? In this second step, we compute sequentially, not using parallelism inside, on a block of size b. So this takes b time, because we use the sequential algorithm for computing the prefix sums within each block. And same in this one, that's even easier. We just add a number, a fixed number to each element in the block. That is another time order b. The interesting part for time is the third part. So here the span is, okay, let's use orange for span. even though that's a little confusing maybe. The span of this step is whatever the span of the prefix sum algorithm is. And we've seen that this is log n prime, the new n that we had before. And because I can just upper bound this by n, log n prime is at most n, is actually strictly less, but we don't bother. So the span of this part is also at most log n. And so we see all steps take logarithmic parallel time. It's the same as before, up to a constant factor. So let's also analyze the work. And here we have to pay a little more attention. What's the work in this case? Well, we spend, that's the number of blocks, and we spend order B time in each block, so that's linear. And the same down here, that's the number of blocks. We spend B time in each block. Total work in that step is linear. And the crucial step for the middle part is the work for the prefix sum was n log n, but we use a different n, so it's n prime log n prime. And if you insert n divided log n, the log just cancels, and there's a minus log term. You'll see the same computation in the tutorials again. That happens to be order n as well. Okay. So we have linear work, which is the best possible because the sequential one also takes linear time. And well, to fill n numbers, you have to spend linear time. There's no way you can improve on this. And we keep the log n time. You can also argue that log n is the best parallel time. So this is an optimal algorithm up to constant factors. Okay. And this is a nice general technique that you first have an algorithm that's not completely there yet. It's not work efficient, but you can bootstrap yourself to a better algorithm by using this one as a black box on some smaller input. This will resurface a little later. Good, deep breath. There's one tiny thing I want to add to this before we close that subsection. Why do we care about prefix sums at all, like other than being a nice toy example? There's one concrete thing that we will use in parallel sorting, and that's the notion of compacting an array. Suppose you have an array of numbers like here. That's the array A, and that contains anything. And we have a different array B, which is a bit vector, and it tells us which of the numbers we would like to keep and which ones we would like to delete. Now, we don't want to physically delete one number after each other. That wouldn't be fast sequentially or parallel because you have to copy things over. But what we can do is create a copy of only the elements that have a 1 in a new array. But we'd like to do this in parallel. So we can do it sequentially easily. You just walk through the array once. That's fine. But we want to do this in parallel. Okay. And there's an easy way to reduce this to the prefix sum problem, where you compute prefix sums of this bit vector B. And then magically, the prefix sums of this bit vector turn into the position that you have to write an element into. That gives you the offset in S that you want. So formally spelled out as code, you compute the prefix sums on a copy of B so that you have B still around. And then you can have a parallel loop where you're only doing anything if you're assigned to a position in A that is 1. So if the original bit vector is a 1, then you're doing something. Otherwise, you just do nothing. And what you do is you write your element into the appropriate position in S. And which position should that be? Well, it's the number of other elements before you that have a 1. And that is the prefix sum in C. Okay? So that's the real use for prefix sums in sorting, at least. We want to be able to do this step. Go from this array where you have some positions marked to another array where you just copied out only the marked elements. Okay, time to wake you up a bit. What is the time for doing this operation that we just discussed? Well, what a mean question. It asks for time and work. Should I show you the algorithm? So when the question asks for achievable, means using the best algorithm we know, right? Of course, you can always do it in a dumper way and spend more time on it. How was it doing with the previous questions? We had 51. Anyone still thinking and or discussing? All right. 5, 4, 3, 2, 1. Many different suggestions, but some definite preferences for some of the options. And the best thing we can achieve is this one. So logarithmic span and linear work. And the reason is, well, it's dominated by the prefix sums. And so it was a test whether you remembered what the time for prefix sums was. And you can look it up the slides before. You can, if you think about this first algorithm with these many binary trees overleaf where we went through rounds, the work inefficient prefix sum algorithm, that one would give you this option. So it's, in theory, the other one's better. To be honest, in practice, sometimes this blocking technique has a little overhead, so it might actually be worth trying for small inputs if the other is faster. But yeah, in terms of asymptotic performance, this is the best we can do.